it's time for us to take a moment to think about free fall and taking a look at some of the kinematics that has to do with the very special case of acceleration, where we're literally just dropping something and allowing it to accelerate due to gravity. So there's lots of different cases where this is one of those types of acceleration that's pretty normal. You've all experienced some of these things in your daily lives, like throwing a ball or catching a ball, playing. I like the famous the free fall ride, like those type of ones that like lifts you up in the air and then just drops you and lets you fall. There's all kinds of stuff where free fall is kind of a part of daily motion. So these little video will have to do with looking at how do we solve free fall problems as simply a subset of our general acceleration kinematics problems. So the first thing to know about this is to kind of think about what happens in terms of speed when you do drop something. So for the purpose of what I'm doing just right now, I'm going to really abbreviate, I guess, or simplify acceleration due to gravity. We're just going to call it 10 meters per second. Now, this is this direction, right? Acceleration due to gravity is always downwards. Regardless of which way the object itself is moving, acceleration due to gravity is towards the center of the Earth. So it's always down. Now, you can say that because it's going downwards, we're going to call that the negative direction, and that's totally fine. It is possible to say that, hey, we want to call downwards positive, and that's all right. So when I'm doing this and I'm using this negative sign here, negative 10 meters per second, I'm indicating the downwards direction. The actual value for acceleration due to gravity is 9.81 meters per second squared. This should be squared right here. Sorry about that. So for the purposes of what we're doing right now, I'm just going to round it to 10 so that we can kind of go through this little thought experiment. As you're doing actual calculations, you want to be using the value of either 9.8 or 9.81 for the actual value of acceleration, again, in the downward direction. So let's think about when you drop something. You literally pick it up and you get ready to let it go. So that first instant that you let it go, its velocity is zero, right? It's at that very first instant when you just first release it, you've just opened your hand, hasn't started, no time has really elapsed yet. That initial velocity, VI, if you want to think about it that way, is 0 meters per second. But at that instant that you let go, it is accelerating downwards. It's about to, right? It's being drawn downwards at negative, basically 10 meters per second squared. So that means that for every second that it falls, it's going to increase its speed by 10 meters per second in the downward direction. So after 1 second has passed, right, the full second, it's dropped a certain amount. So now after 1 second, its new speed is now 10 meters per second, downwards. Again, downward direction. And its acceleration is still 10 meters per second squared. That's actually not going to change. Acceleration due to gravity is always negative 10 meters per second, again, if we're just approximating it for the purposes of this. So after the second, t minus 2, right? Now what's happening? Now it's going to increase by another 10 meters per second. So every second that it falls, it's going to increase its speed by 10 meters per second. So after 2 seconds, it's going 20 meters per second. After 3 seconds, it's going 30 meters per second. After 4 seconds, 40 meters per second. And after 5 seconds, it's going 50 meters per second. And again, now we're talking about the negative sign, just means it's going downwards if we define that as the negative direction. But its acceleration is constant. It's the same every single time. Meters per second squared, negative 10 meters per second squared, negative 10 meters per second squared. So again, if I could write second squared, there we go, sorry. So the acceleration is constant. The velocity is changing, and every second that it goes down, it increases its speed. So again, pretty straightforward in terms of understanding what that means. You're just literally increasing it 10 meters per second per second. That's what that means. But what happens if you throw something up in the air? Now, this is a little bit of a different situation, right? Now you're throwing it this direction. It's going to go up for a while, and then eventually it's going to come back down, right? That's, the law of gravity and all that stuff. So now what's happening in this? Take a look at what we've got here. Now you've got a VI, right? This is our initial velocity, and it's going upwards at 20 meters per second. You're throwing it up in the air. And our acceleration, again, is always negative 10 all the way down. Every single time, it's going to be negative 10 meters per second, just for this thought experiment. Again, we're rounding it. So at 1 second, what happens when you throw it up in the air? Well, you throw it up really fast, and as you go up, it slows down. It'll eventually come to a stop, And then it'll start speeding back up as you go back downwards, right? You've seen this. Otherwise, if you threw it up and it didn't slow down, it'd just keep going up forever, right? It's got to slow down at some point in time. So you can kind of see how this works. It's accelerating at negative 10 meters per second downwards, right? So that means after 1 second, if it started at 20 meters per second upwards, after 1 second now, its speed is 10 meters per second. I've changed it by negative 10, right? I've removed 10 meters per second from this. After the second, we have now achieved apogee. You're at the top. You've gotten to the top of the flight. It's going up at 20 meters per second, then 10 meters per second, and then it stops. And then it's going to change direction and go back downwards. So now as it's going back downwards after that third second, now it's going to go negative 10 meters per second. And then it's going to go negative 20, negative 30, etc. Meters per second, meters per second. So remember what the signs mean here. This means that it's going upwards. This means it's going upwards. This means that it stopped. This means now it's starting to go back downwards. It's changing its direction and its velocity vectors are increasing each time. That's all that it means. So again, think about what the difference in signs mean. You'll hear me talk about this a lot, that the signs, positive and negative, is really critical to identify the direction of motion. So if your velocity vector is upwards, if we're going to call this as positive, then our acceleration vector is going to be downwards. It's going to be negative at negative 10 meters per second. So again, just got to be very careful about how you identify the positive and negative axes. All right, so moving on. So what are some of the assumptions about this? Now, you guys know that if we were to drop something every 10 meters per second, if it got faster every single time, eventually things would be going, hundreds to thousands of meters per second. It's crazy to think about that. So there's some things that really don't work. And there's a big joke that we have in physics called the joke of the spherical chickens. I don't know if you really want me to tell the joke right now, but I can tell it in here in a fairly quick moment. As we are dropping things, you know that idea that even if we just dropped it and it went negative 10, negative 20, negative 30, negative 40, negative 50, negative 60, etc., it can't keep going forever. At some point in time, you do, in the real world, achieve maximum velocity. That maximum velocity, by the way, when you're skydiving, it's called terminal velocity. It's a horrible name, right? Don't like talk about terminal stuff when you're skydiving. Terminal velocity means you're reaching your maximum speed. Why do you achieve terminal velocity? Well, because air is a thing. That air creates friction. So even though you're trying to fall and you're getting pulled down to the earth, there's an upwards force from the air. And eventually these two things balance each other out and you achieve constant velocity, which is called terminal velocity. That's that maximum speed that you can get. I don't know if you've ever noticed this, but if we fall, from a very short height, we're going to break something. But have you ever tried to drop an ant and kill it? You can drop a spider or an ant off of like the hugest height and it just bounces. Like, dude, why doesn't it do that? Well, it achieves terminal velocity for its size. The amount of speed that it can get is actually quite small. Same thing people talk about. Well, if you dropped a penny off the Empire State Building, you could kill somebody with it. No, you can't. Not a real penny, not in the real world, because the penny eventually is going to achieve terminal velocity, and that speed isn't quite enough to kill you. It's enough to hurt. Oh, trust me, you'll feel it. But it's not going to bore through your brain or whatever like that. It just isn't going to happen. The penny itself has enough air resistance that it'll slow it down. And that's what our spherical chicken assumptions are. One of the big things that we do is that we assume that there is no air resistance. TANCE, is ignored. So I'll tell you what the spherical chicken is here. It'll make our video a little bit longer, but I'll tell you what the joke is. So our big assumption here when we're doing this is that air resistance is ignored. We know it's not. Okay, we know air is a thing, but for the simplification of what we are doing in physics right now, we are indeed going to ignore air resistance so we don't have to worry about that upward, negative, positive acceleration canceling each other out. So here's the story of the spherical chicken. I'm going to say it very briefly. There was a guy who was a chicken farmer, chicken farmer. And one of the biggest issues with farming and ranching chickens is that when you try to bring them to market, you have to pluck them. So you have to be a chicken plucker. And it's a time-consuming process. It's cruel for the chickens. It takes a lot of time and effort and energy. Really cutting into this particular chicken rancher's bottom line. So he was trying to figure out a more efficient way to have a a chicken plucking device of some sort. So he wanted to invent a chicken plucking machine. So the first thing he did was he called his biologist friend and said, hey, I need to invent a chicken plucker. And the biologist is like, what? Okay, let me work on that. Biologist came back another day or two later to try to come up with this chicken plucker, and couldn't do it. The biologist was like, you know what? It's too cruel to the chickens. We can't get it to work right. There's just no way to do a chicken plucking machine that's really going to save you any time and money over what you're currently doing. So I can't help you. Farmer didn't want to give up, so he approached his friend, who was now an engineer, and said, okay, my engineer friend, I need to have a chicken plucker. Can you make me one? And the engineer's like, of course, I can make you a chicken plucking design. Give me some blueprints. I'm going to go get CAD. I'll be back with you in a week. So, a week later, engineer comes back with all of these just crazy complicated blueprints, just pages and pages of sheets of ultra complicated diagrams. And the rancher's like, what in the heck am I supposed to do with this? Engineer's like, no, it'll work great. It'll just take a building that's bigger than your barn. So we'll have to build you a new enclosure. Let me get you back to you with some blueprints on that too. And the farmer's like, no. Sorry, engineer, my friend. Yeah, that's great, but that's too complicated. I know it'd work. It just isn't going to work for me. So the final thing is the rancher, approaches his last friend and says, all right, I don't know what I'm going to do, but I'm going to approach my last friend who's a physicist. He says, okay, my physics friends, can you come up with a chicken plucking, a machine for me? I need something that's not cruel, that's cheap, that's fast, that doesn't take a machine bigger than my barn, et cetera. What can you do? The biologist let me down, the engineer let me down. Physicist, please, can you help me? Physicist is like, yeah, sure, give me 5 minutes. You got a cocktail napkin? Let me draw this out for you. And he literally starts sketching it out on the piece of paper. He's like, okay, hold on. Yeah, here it is right here. And yeah, go. And the guy's like, how did you solve my problem so quickly? That's brilliant. What an amazing design. It's cheap. It's fast. It'll pluck all my chickens in a minimum amount of time. What did you do? And the physicist says, well, in order to make this work, we have to make a couple assumptions. So first thing is we're going to assume that the chickens are a sphere. And then after that, everything's easy. And that's the joke, is that chickens are definitely not spheres. That a lot of times in physics, we very much oversimplify things, at least at first, right? To try to get our brains around complicated natural systems. So even when we did motion diagrams, right? And we represent motion diagrams with stick figures. And then when we represent with a particle, just a dot, we know that thing isn't really a dot. We know that there's more complicated motion to it. But it can simplify our expression, our calculations of it, our drawing of it. And so we joke about a lot in physics about spherical chicken assumptions that we know aren't really true, that they aren't realistic, but they really help us simplify the math. So you'll hear me talk about spherical chicken assumptions all the time. And our big spherical chicken assumption that we do in acceleration problems is we're going to pretend like there's no air resistance. We know there is, but for the purposes of what we're doing, we're going to pretend like we're going to drop this spherical chicken in a vacuum, and it'll make all of our everything else work out more easily. So that's my fuss about spherical chickens. Sorry, it's not the greatest joke, but it works. So when we are talking about our free fall givens, when we're doing our acceleration problems, in the next video, we'll do some more sample problems. There's a few things that we need to know. Number one, we're going to assume that acceleration is due to gravity and gravity alone. I.e. free fall. We're going to assume that gravity is the same everywhere on Earth. It is not. There's actually slightly different, amounts of acceleration depending on where you are. High elevation has less acceleration than lower elevations. It's measurable, but it's not a bunch. So we're going to pretend like it's always 9.8, right? No matter where it is. Acceleration due to gravity is different on different planets. So if I start moving you to Jupiter or something like that, you do have to take that into account. But on Earth, we're going to pretend like our spherical chicken assumption that gravity is the same. We do abbreviate acceleration due to gravity, by the way, with either the letter A, just for acceleration in general, or you'll see a lot of times we just use the letter G to kind of specify that, hey, this is acceleration due to gravity only, and therefore you know what the value is, 9.8 or 9.81 meters per second squared. So just be aware that, don't let that throw you off. If you see an A or a G, they mean the same thing. Second thing, or third thing, I guess, is when we are talking about our free fall, it is really important to define our directions. Our coordinate system is really important. You will see some people say that acceleration due to gravity is 9.81. Some people will say it's negative 9.81. It depends on how you define it. Remember, the negative sign is the direction. Acceleration due to gravity is that way. If I define that this way is positive, then I can say acceleration downward is plus 9.81 meters per second squared. That's fine. If I say that this direction downward is negative, then my acceleration is negative 9.81 meters per second squared. So the defining our axes is really important. And it's one of those things that students miss a lot, that I can call down positive, but if I'm throwing something upwards, then I have to have a positive and a negative direction. So just be really aware of that. Again, we're going to assume that acceleration is consistent and that it begins the first instant that you drop it. That acceleration due to 9.81 is always happening. So like this calculator is ready to accelerate at 9.81 all the time. It's not accelerating right now because I'm exerting a force on it and holding it up, but as soon as I let it go, instantaneously, full acceleration. You can't see it, but it's there. And then the last one, our biggest spherical chicken assumption, is that we will always assume no air resistance. You'll see the language that's in there. If you want to do air resistance, you just have to add some extra forces. We'll get there in a later chapter if we do that. Okay, so there you go. Introduction to acceleration due to gravity and free fall. And in the next one, we'll do some example problems. Okay, enjoy that. Bye.